Good afternoon. My name is Juan Carlos Melgar. I'm an associate professor with Clemson University in South Carolina. And I'm going to talk about a study that we carried out here in collaboration with the University of Cordoba in Spain. Kelly Nascimento, the second author, she was a PhD student from the University of Cordoba that came to Clemson to do research abroad study. And back in Spain, she was working on the effect of silicon in improving tolerance to abiotic and biotic stresses in olive trees. But here in the southeastern United States, peaches are the main fruit crop, and we were interested in doing this research on peach. So that's the title of our project: Silicon Improves Water Status of Young Peach Trees Under Drought Stress. Just as background information, this is what peaches are grown in the United States. The main producing state is California by far, with big difference. But then we have a lot of peaches in the southeast, a lot of acreage here in South Carolina and Georgia. We are the second and third producer respectively. And just so that you can see, we are right here in South Carolina. We have a subtropical humid climate, and it typically rains enough to support the needs of the crop. Although, of course, there is seasonality. And for example, for mature trees, there is a need for supplementary irrigation during the last fruit growth stages. However, when we talk about young orchards, as you can see in this picture, there is no irrigation. It's the common practice here in the region is that young trees do not start being irrigated until the third leaf, until the third year, which is when growers get the first harvest. And so again, that's most years that's not an issue because it typically rains enough. But as you can see here, either because of regional climatic oscillations, we have El Niño, La Niña, growers and researchers are also worried about climate change. We have seen how over the last 20 years, there have been several years with exceptional, extreme, and severe droughts, like in 2012, 2008 and 9, and 2002. So, of course, these drought events can affect, the trees are being formed during these years, so they can affect future production if they do not have any irrigation. And so that's where silicon comes in, as it has been widely reported that silicon alleviates the plant water status and water balance under different stress conditions, including drought, in both monocots and dicots. There are many more studies with annual crops and very little studies with fruit trees. Silicon is actually very abundant. It's the second mineral element more abundant in the Earth's crust. And all plants contain silicon in their tissues, although we know that there are some plants that contain or accumulate more than others. Those species that have more than 1% of silicon in their tissues are considered accumulators. And examples are rice, wheat, and tomato. And those that are below 0.5% are considered non-accumulators. And the ones in the middle are intermediates. And interestingly, most fruit trees are among those non-accumulators. Here under other prunus, we do not have any values for peaches particularly, but there is this study that considered some wild cherries and some of the prunus, and values are between 0.28 and 0.5. That's the only reference we have. In the soil, silicon is found in the form of silicates in quartz, feldspar, and micas, and that form is not available for plant uptake. So when these minerals are go through weathering, it's released to as silicic acid or monosilicic acid, and this is a form that plants can uptake either passively through mass flow or actively mediated by silicon transporters. And I'm using here a drawing of a rice plant because rice is, again, one of the species where silicon has been more studied. So when applied to the soil, silicon application has been found to be involved, being involved in improving hydraulic conductance by upregulating aquaporin gene expression and also concentrating potassium in xylem sap. Many studies where silicon has been applied to the soil conclude that silicon actually improves plant water status by increasing root water uptake rather than by reducing water losses. However, since our young trees are not irrigating the field, trying to think of a practical way, and also because there are some articles in annual crops saying that silicon applied foliarly can reduce transpiration rates, our focus was actually on studying its effects on tree water status and transpiration. Interesting, the literature says that silicon in the leaves, silicon tends to accumulate underneath the cuticle on top of the epidermis. And for that reason, we hypothesize that it could help reducing cuticular transpiration. And so our objective was to evaluate the efficacy of foliar applications of silicon for improving water status of young peach trees under drought stress. So we had a study with 2-year-old peach trees grown in pots under a shade house. And again, trying to think of an applied result of our project. We did not, like most studies show how people apply silicon to the plants either through irrigation or foliarly, trying to have kind of load the plant with silicon before the stress comes. But from a practical point of view, that wouldn't be something that our growers would be doing because you don't know when a drought is coming, other than for the next 10 days. And so you cannot do several applications, weekly applications before a drought comes. We thought that it would be much more practical, even though it was also more risky because there isn't a study that way done. Having the trees stressed, and when we have the differences between the different stresses, then we would apply silicon and see how it would protect against that. And so we had well-watered trees that were receiving 1 liter a day, and we have deficit irrigation trees receiving 50% of what the well-watered trees were receiving. You can already see here how these trees started developing water stress, water deficit symptoms. And that, when we saw that we had 2 separated treatments, that's when we started with applications. We did weekly applications of silicon using a backpack sprayer. And we have controlled trees that did not receive silicon in both well water and deficit irrigation treatments. And then we had trees receiving 20 milligrams per liter of silicon and trees receiving 40 milligrams per liter of silicon. Again, these were weekly applications, and we did applications for 1.5 months since the moment when we saw that trees were under 2 different irrigation conditions. And then our measurements included tree water status. We measured midday stem water potential using a Scolander type chamber. We also measured gas exchange using a Lycor portable gas exchange analyzer. And we collected samples for leaf mineral analysis. We did silicon concentration and potassium concentration. We did all these measurements weekly throughout, since the beginning of the silicon applications. And then if we start with results, for tree water status, well, I'm showing here stem water potential in bars and days from the beginning of the treatments. For both treatments, we did not have interaction in this case. So if we see the well-watered trees, we have the black line is the control, the green line is the 20 milligrams per liter, and the blue line is 40 milligrams per liter of silicon. So if we see the well-watered trees, and there were no differences, significant differences between treatments. For peaches, we always consider about minus 15 bar or minus 1.5 megapascals. It's kind of like the line where the stress starts, like when we go under more negative than minus 15, that's when a tree starts being stressed. And then for the water deficit trees, we saw how they were below these well water values. The control, no silicon treatment, had lower values than the 20 or 40 milligrams per liter, the blue and green lines. As you can see, these control ones were close to or around minus 20 bars, minus 2.0 megapascals. And that means trees were severely stressed. However, those trees that received silicon, even though they did not reach the well water levels, they were in a much better position than the control trees. When we look at gas exchange, we saw there was an interaction between the irrigation and the silicon treatments. And we can see here how for leaf transpiration, for example, of course, well water trees had a higher transpiration than the water stress trees. But interestingly, we saw how there was a reduction in the well water trees, in leaf transpiration of well water trees for those that receive the higher concentration of silicon versus the control. However, we did not see that difference. The trend is in there, it's a numerical difference, but it's not statistically different, the leaf transpiration of these trees versus the control. Same thing we saw for stomatal conductance. Trees receiving higher concentration of silicon had lower stomatal conductance than well water trees. However, again, the trend is that we did not see these differences for the water stress trees. We think this is because, okay, the literature reports that up to 20% of leaf transpiration could be cuticular transpiration. So we think that that layer of silicon there, the silicon being deposited underneath the cuticle, it's reducing cuticular conductance and cuticular transpiration. And the problem is that when we measure with the Lycor, we are not able to separate what's cuticular, what's stomatal. I mean, we just have leaf transpiration numbers, like overall numbers. And the stomatal transpiration, stomatal conductance is by far a much bigger number than what's going on through the cuticle. So we think that these stomatal values have overshadow what's going on here. And that's especially for the case where you have very little transpiration. Again, it would be very interesting to know how much of these was cuticular transpiration. But that's the component that we don't know. But seeing that numerically, we could see that trend, and that was happening when you have a higher value, made us think that that could be the reason why we saw a better status, but we still did not see these numbers for gas exchange following the tree water status numbers. Now, we did not see any differences in CO2 assimilation or in water use efficiency. Then when we look at mineral analysis, there was also an interaction here. We analyzed silicon concentrations. We did that weekly, but I'm here only showing the numbers at the end of the experiment. And we could see how the well water plants did not increase significantly the numbers in those trees that received more silicon. However, the water stress trees had higher numbers than the well water trees. And interestingly, and I'm not sure if this is an artifact or if there is something behind here that needs to be studied as well. For leaf potassium, we saw the same trend. We saw how there was a higher concentration of those leaves from water stress trees that receive higher silicon. Again, this has been seen when silicon is applied in the soil with irrigation, but but we have never seen it for leaves that have received silicon. So it would be interesting to see, again, I mean, these numbers are really, differences are not huge. Numerically or statistically, they make sense, but we are between 2.9 and 3.2. In any case, it would be interesting we're looking forward to repeating this experiment and seeing if this is confirmed, because it would be very interesting to understand if that's true, to understand the mechanism on how potassium it's increasing when you're increasing silicon. So the take-home messages are that water stress trees receiving foliar silicon had better water status than water stress trees without silicon. We did not see significant differences in leaf transpiration or leaf conductance, and we would need to, I mean, other than these minor differences that I mentioned before, but we will need to assess if an improved water status may be actually caused by reduced cuticular conductance and cuticular transpiration. And then foliarly applied silicon increased leaf silicon concentration, as we were expected, and no changes, I mean, that was for water stress trees, and no changes were observed in well-watered trees. I would like to acknowledge the University of Córdoba, or we would like to acknowledge the University of Córdoba for the fellowship that allowed Kelly, on the left, to do her research abroad study for her PhD. Also Yaravita, who provided the silicon formulation, the Master Fruit Research Farm crew for the help with the study, and also the graduate students that helped Kelly with the study. And this is all I had. I would be glad to take any questions you may have. Thank you.